To project a vector on a line, then you take the vector, and then first we take a vector on this line, parallel with this line. So we take, for example, this blue vector here. Then to project that vector on the blue line, we take a line perpendicular to this line that intersects the tip here. So we project down this red vector like this. Then we get this yellow vector here. So this yellow vector, that's the projection of this red vector on this line. And this line is given by this vector, because this is a vector that's parallel to the line. And we call this vector here, the projected vector, let's call it UV. So it's a U projected on V. Here we have an angle called theta. So this is how the figure looks if theta is less than 90 degrees. For an angle larger than 90 degrees, we instead have this figure. Then the projected vector is instead given by this vector here. So we project down here instead. So that's what meant by projection of a vector on a line, or projection of a vector on a vector. So this is a projection of the red one on the black line that is given by the blue vector parallel to this line. The following formula here gives the projected vector in terms of u and v. So let's first see an example, and then we will prove this formula. So let uv be 2, 2 and v 3, 1. Then from the formula we have u scalar product or dot product with v divided by the length of v squared multiplied by v. Putting in these numbers here, so we have 2, 2 dot product 3, 1, and then the length of v, that's 3 squared plus 1 squared. Then we have the square root, but since we also have the square, that cancel. So we are left with this. And then we have 3, 1. Calculating this, we get 2 times 3 and 2 times 1 divided by 10. So 6 plus 2, 8 tenths times 3, 1, which can be simplified to 4 fifths times 3, 1. We can leave it as this. We could also multiply in, then we get 12 fifths and 4 fifths. So this is the projected vector we get if we project u on v, or on the line given by v. Now we want to prove the formula we had for the projection. If we start with dividing v with its own length, then we get the unit vector in the direction of v, with length 1 pointing in the same direction as v, so here somewhere. Now we have that the projected vector we are looking for, it's pointing in the same direction as this one. So if you multiply this vector with the length of the projected vector, we will get the projected vector. So the projected vector here is this vector times its length. And here we have expressed the unit vector. So substituting it here, we get this. This can be written as like that. We know v, we know u and v. This one we don't know, so finding this length, we can do that with trigonometry. From the figure here we have that cosine of the angle, cosine theta, that's equal to the length of this one, which is the length of the projected vector, divided by the length of the hypotenuse, which is length of u. This one we can write like this. So if we solve for that, we have that this. Let us multiply this equation with v on both sides, with length of v, that is. Then we get the following. Now we can notice that what's written here is the scalar product of u and v, or the dot product of these two. So we have dividing on both sides with the length of v, with this, it cancels on the left side, and we get this. That means that we have finally found the length of the projected vector expressed only in u and v. So now we can replace it here in this formula. So there. And then we get that the projected vector, this one, is equal to this. And here we take that. And here we have fraction divided by this 2 times. So this will just become the square of the length of v multiplied by v. And then we have proved our formula.